Your life is made up of multiple parts and systems, and things can get a little complicated as all the different parts of your life move and try to integrate over time. Solving complex problems is exactly what systems engineers do for a living, but not all are made equal. What can we learn from their methods to solving the complexity in our own lives? Hello everyone and welcome to the Engineering IRL podcast for engineeringinreallife.com. This is revision 36 of the show, and today we will be breaking down the different types of systems engineering. Now, systems engineering is one of those disciplines where you can track its origins, but at the same time, it's not very clear what it means to be one, much less what one's day-to-day would look like. The cool thing about systems engineering is that there's a problem-solving methodology at its core, and is specifically used for complex solutions. If I can break this down for you, it might just be what you need to think about to solve some of your own problems, whether if you think it is simple or complex. Let me start by quickly listing a few types of systems engineers. Think of it like there are many types of engineers who solve different problems for different industries: civil, aeronautical, mechanical, electrical, software. And then within those worlds, at some point, the solutions will have to implement different products, designs, processes, and systems to solve it. It's this interface, multiple moving parts type scenario where systems engineering actually comes into play. So back to some of the types. I'll just list them. Biological systems engineer, computer systems engineer, control systems engineer, IT systems engineer, software systems engineer, which extends to site reliability engineering, space systems engineer, enterprise systems engineer, embedded systems engineer, safety systems engineer, security systems engineer, weapon systems engineer. Not bad. The list goes on, and a lot of them sound intriguing and interesting. So the question becomes, what's the difference between these different types? And then, are there similarities? And can they move across these fields? So the use of the word systems isn't just coincidental in that it's a generic term for systems of each of the branches of engineering. It's quite literally an interdisciplinary field, by definition. It's in the name. You can't actually do the job and just focus in on one technology. The whole point is like a holistic view, like a bird's eye view. Mix that with the ability to have a microscopic view on any of the given technologies, and the idea is to be able to switch between these two views and make sure everything will align. This is why the generic systems engineer doesn't really do anything on its own, per se. It needs to be embedded within another discipline of engineering, and more often than not, multiple disciplines. So if you go to a job site, you can see many jobs for systems engineers, like seek.com or something like that. But when you look at the education side, there's not as much that is offered outside of the context of a traditional engineering discipline. Don't get me wrong, they are there, you can study them, you can study systems engineering, but there's two lenses to look at this. So the first is a system-centric lens. So think of this as studying systems engineering itself, the related skills, the methods. And the second one is a domain-centric approach, systems engineering topics on top of another major or a domain. And this reflects the real world, except that whether it is looking for something more system-centric or domain-centric, the job titles are usually some form of just systems engineer. Okay, wait. So then what's the differences? What's the similarities? Okay, the similarities are all to do with it being interdisciplinary and managing complexity. At the end of the day, because you're dealing with situations that involve different discipline and domains, it automatically creates more complex situations. So by default, it's already more complex. Now, it's like when you have one group of friends here, say your high school friends, then you have some family childhood friends, and then you have some university friends and work friends, let's say. Okay, now, when you hang out with any one of those groups, it's pretty simple on you socially, right? Okay, I know sometimes it isn't easy, but it's kind of clear you know how you behave within that group. Now, if you organize a party, let's say your birthday, where you have to integrate all these different groups into a singular party, where you host and have to mix and match your social interactions within all of these, it's a little more complex. Now, depending on the number of people, this increases the complexity, right? So the more people there are, then the more complex the situation becomes. And then let's say the party is not your birthday now. It's now your wedding. You have to integrate the same set of complex friendship systems of your significant other as well and combine these two bodies of friends, right? So you see where I'm going with this. You interacting within any one of these individual groups is relatively simple, whilst integrating the multiple groups together makes it a little more complex. Now, if you were to think about making a helicopter work, one that you would be confident enough that a human could sit inside, be lifted hundreds of meters into the air and not be dropped to their death, this would require a combination of parts, systems, technologies, science, and humans to do, let alone deadlines, budgets, but you get the idea. So the job is, will all these parts and parts of parts and their overall systems work together? So you're jumping between like a macro and a micro view. And this is why, whilst there is a methodology there to help us achieve this, it helps tremendously to know a thing or two about all the types of systems or parts or steps involved that make up that bigger picture. So now imagine going back to the wedding example, except in this case, you don't know who you're marrying, and you don't know any of their social circles, but the wedding must happen without a hiccup, or else you get cursed with biting your tongue every time you speak forever. I needed some insert bad thing example here to complete the example. But anyways, in that scenario, it is a lot harder to make sure things go smoothly because you don't know anything about one of those systems you're trying to integrate in the first place. So hence it is useful to know a thing or two about the underlying systems and technologies. Cool. So, okay. That's a little bit to digest. It's a little bit to unpack. But all I've done so far is to say, here's some systems engineering types, and that the similarities are that it is interdisciplinary and it exists to help solve complex problems. That's it. Which means the differences all lie within the word prior to systems engineer. So weapons systems engineer, embedded systems engineer, control systems generally give you the domain and the technologies in the name itself. And then one more distinction depends on the industry and the company. So it's kind of like a matrix of sorts, depending, this will dictate where on that spectrum your day-to-day would look like. So it varies from creative thinking, very high-level design, to critical thinking and detailed-oriented assessments, from heavy office work to boots-on-the-ground field work, from project management, communication focus, to a very technical, concise articulation. Big range. Now, onto how it might actually solve these problems. Well, there's definitely an overarching methodology, but depending on what type of engineering, as I said, will mean where along that methodology you might spend most of your time on. With that being said, let's take a quick look into a high-level methodology. And, it'll vary, of course, but this can be broken down into 4 main stages. Number 1 is a task definition. This is an informative definition. Number 2 is conceptual stage, cardinal definition. Number 3 is design stage, formative definition. And number 4 is an implementation stage, manufacturing definition. In some cases, that same kind of breakdown might look like this. 1 is analysis, 2 is design, 3 is build, 4 is install and commission. So these 2 scenarios may be dissected or categorized differently. But the other reason why I bring these 2 up is one is kind of product focused and the other is more service focused, or system integration focused. So the former getting you to a point of making a product, and the latter is more focused on integrating a system. So I'll break it down a little more. Okay. In the earliest stages, the whole idea is to try and define the problem, roughly in the beginning. So task definition and analysis both are looking at the requirements, the problem statement, the goal of the project, all that stuff, clarifying what should be included in the scope in the first place, who is responsible for different parts of the picture. So step 1, define your problem. Okay. The next stages come to starting to conceptualize a design, potential solution options, and what that might look like for all parties involved. So you're looking at your scope, and then we'll have that placed within context of other things that are related but are out of scope. And that kind of shows where they interface and where the lines are. For example, your solution might propose a computer or a PLC to be installed. Within scope might be a power supply, but the source of that power, the electricity, might be out of scope. You would still show this connection exists, but might show a line that says this part of the equation belongs to us. So I'll provide the physical computer, the cable of the power supply, and I'll plug it into the wall somewhere. And that part behind that wall, or behind that port connecting to the electricity, belongs to a third party. You start with a conceptual high-level design and ideas, and you progress to a more detailed low-level design. This is no longer just saying this box will be used. You are now saying specifically this box will be used and port 2 of this device will be connected to port 3 of that device, specifying sizing, power, technology, protocol, IP ratings, the configuration, all the variables that could impact the overall design. Once that's done for all the individual parts, you go back to the more conceptual look, right? And then you see if all the parts would connect together, not just that they're compatible. You look at a sheet, they're compatible, yay. But also, are they still mapping back to the scope and requirements defined in the very first step? So that's a high-level conceptual design through to detailed design. Here you also have like schedules, milestones, resources, things like that. That'll start coming together. But you can't just think of the system coming together at a technical level. It's like having money for that wedding, but you haven't got a partner yet, or you haven't booked anything yet. So, the wedding's still not going to happen even though you've got that money, one part of the equation. So this can all get a bit confusing and actually be quite bland. But the key here is using models. So models are a key tool of systems engineers, allowing all the moving parts to be defined, all to have a home, and all different processes and people can quite literally be on the same page. They say a picture can say 1,000 words. And if you remember back to episode 16 of the show, we say that one drawing can solve 1,000 problems. So just to touch on some of these tools, we have function flow block diagrams, data flow diagrams, use case diagrams, system architecture diagrams, model-based design diagrams, systems modeling language. There's more, but that's it. That's a good start. You can then use these diagrams to start framing up the different technologies that address the problem. Compare the solutions, and the system engineer can decide what's best, right? These drawings are super useful when iterating through design options and finally landing at a refined solution. Anyway, next you have a build stage, and this is where you put together the initial parts of the system, but in like a factory type setting. It's not going to solve the actual problem yet, but we're putting it together to test that after building it, it's of good quality and meets the requirements. And the implementation stage / the install and commissioning stage is really putting it to actually do the job. So both of these phases have many different tests to pass and get through, and typically they include benchmarks as defined in the design phases. Factory acceptance testing, unit and integration testing, as well as site acceptance testing are the types you'll hear about in these phases. But essentially there are audits and checks at each stage. Think of these latter stages as the execution phase, the day of the wedding, and the days leading up to that are like setting everything up. Whew, okay. That's quite a bit to unpack, but you might have noticed I jogged through the later phases, and that's not because I got tired, but it's really because most people understand the execution phases, the going through the motions, that sort of thing. That's the action that commits to memory. So you know how to do that. You work well in this realm every day, in life, always. You can put this level of detail work in everything you do if you want it, but it wouldn't be feasible. But it does mean putting in a little effort in the pre-work would make a huge difference in making sure things will work. In a big complex situation, there is so much resources and investment involved that you really, really want it to work. And the best method we have for doing that is the systems engineering approach. Now, you might pull off one event without spending much time on it. It's not likely though, but could you do it again? Like, what if the requirements slightly changed, or some variables all of a sudden didn't exist? It has to be repeatable, and it has to last more than one day. Most life expectancies of a complex system would be more like 10 to 20 years. Heck, look at Sony PlayStation. They're trying to design something that will last more than 7 years. That's the previous system. Look at a space system or a car. It's not designed for you to drive once per trip, right? So anyway, the point is, if you want to have sustained success, you need to spend more time on the planning, preparing, and designing than you spend on the executing. Now, don't get me wrong, you need both. Okay, so for the procrastinators out there that have been planning and haven't taken action, this does not apply. When you design but have no execution, that's even worse because you've invested all this time and you've taken no action. Most people's problems seem to be spending too much time on only one of those things. So procrastinators only have ideas, and overworked with no success types don't spend enough time planning and designing. The ones that do both benefit from both designs, both parts being informed by the lessons learned from executing. Okay, and the execution improves because the designs were better. See what I mean? So, before I wrap things up here, let me drop in some top skills in addition to the technical problem-solving skills. These are skills anyone can improve upon for systems engineers. Number 1, communication skills. Number 2, ability to serve as a technical project manager. Number 3, width of knowledge and familiarity with all the technologies. If you want to solve problems, and more complex ones, you'd best believe you should improve in these things, systems engineer or not. Simon Ramo, who is considered by some a founder of modern systems engineering, said it best. Systems engineering is a branch of engineering which concentrates on the design and application of the whole as distinct from the parts, looking at a problem in its entirety, taking account of all the facets and all the variables, and linking the social to the technological, which is a nice way of putting it. Now, at the beginning of the episode, I did say breaking this all down for you might actually help you. So, one lesson is to ask the right question / scope properly in order to solve anything slightly complex. Using the Socratic method. Ask, ask, ask. Question your assumptions is the most important part. Are there some answers you're not happy with in your own life? Well, could it be that you're not asking the right question? Could it be your expectation was not met because you didn't define the scope clearly? I'm unhappy because my job sucks is a terrible definition, and your solution of complaining about it is a terrible answer. Dig deeper. Question yourself, why, until you get down to what the requirements would be for your job not to suck. Not the best example, but you get the idea. Another thing to consider is the fact that the key soft skill for a systems engineer is communication skills. Dealing with all the types of stakeholders and needing to know what their drivers and their pain points are means that so many problems arise to ambiguity. Okay? You need to clarify things. It's not as easy when there are maybe personal feelings involved or the drivers, but not saying something generally winds up costing more in the end. It can be hard to explain the technical in a non-technical way, and the drawing tools are a decent way to start. There's a book by Aristotle. It's called The Art of Rhetoric, which was written to help smart people who couldn't convince anyone of anything to save their life. The key is understanding your audience. It's not good enough to be right, So audit yourself. You are a system. Your ideas are a system. Your peers are a system. Your work is a system, and society is a system. So take a systems engineer approach and understand that to integrate any system, big or small, you better be sure you are asking the right question and that you define the scope clearly.
This is the Engineering IRL Podcast, a place for engineers in the real world. We try to break down engineering concepts and figure out how to apply them to real life. Let's become better problem solvers, better engineers. This is your host, Andrew Sario. Let's begin.